Here we're going to look at what I think is a pretty hard problem that was shortlisted for the 1988 International Math Olympiad. So we want to suppose that alpha is the greatest root of the cubic polynomial x cubed minus 3x squared plus 1 equals 0. Then we want to show that if we raise alpha to the power of 1988 and then take its floor, that number is divisible by 17. So we're going to use a couple of tools in order to find our solution, in order to produce our solution. So if you guys want to try to solve this on your own, I would say maybe these are some good hints. The first one is Vieta's formula. So this relates the coefficients of a polynomial with the roots of a polynomial. So we have if x cubed plus px squared plus qx plus r factors like x minus alpha times x minus beta times x minus gamma, then alpha plus beta plus gamma is equal to minus p. So that's what you get if you calculate the coefficient of x squared on both sides of this equation. Then alpha beta plus alpha gamma plus beta gamma is equal to q. That's what you get if you calculate the coefficient of x on both sides of this equation. And then finally, alpha times beta times gamma is equal to minus r. So that's the constant term on both sides of this equation. And then this actually implies something that's pretty strong, and that is if p, q, and r are integers, which in our case they are, and you have a symmetric polynomial in the roots. So what I mean by a symmetric polynomial is you've got a polynomial where if you switch any of the variables in any way, you end up back with the same polynomial. Then that symmetric polynomial in the roots is in the integers. Obviously, if you've got coefficients in the integers. You might say, well, why is that? That's because these things on the left-hand side generate what is known as the ring of symmetric polynomials in 3 variables. So you got a symmetric polynomial in alpha, beta, gamma. You can express it in terms of alpha plus beta plus gamma, alpha beta plus alpha gamma plus beta gamma, and alpha beta gamma. And then since you've expressed it in terms of those, you've really expressed it in terms of p, q, and r, which are integers. So what you have is in fact an integer. So our next tool will be the intermediate value theorem, and we'll use a computational technique based on the intermediate value theorem known as the bisection method. And that says if f is continuous on a closed interval a, b, and f of a and f of b have opposite signs, so one is positive and one is negative, then there is a c on the open interval such that f of c is equal to 0. So in other words, you've got a root between those two endpoints. That's because a continuous function cannot go from being positive to negative without passing through the x-axis, or vice versa. And then finally, we've got this thing called Vermos little theorem, and that says that if p does not divide a, then a to the p minus 1 is congruent to 1 mod p. Okay, so there's a bunch of hints here, and like I said, this problem's pretty hard, but if you want to give it a go with these hints or otherwise, now's the time to do it, and then we'll look for a solution. Okay, now we're ready to look for a solution. And the first thing that we're going to do is estimate the value of the roots. So we have some sort of idea of the greatest one versus the size of the ones that are smaller than the greatest one. We're going to do that using this intermediate value theorem, which was our second hint, and the bisection method. So let's maybe set f of x equal to our polynomial. So that's x cubed minus 3x squared plus 1. And then let's maybe put a number line up here and then just start evaluating f at certain points, finding out if it's positive or negative at those points so that we can come up with an approximation of the roots. Okay, so let's first notice that if we take f and evaluate it at 1, we get 1 minus 3 plus 1, so that's equal to negative 1. So that's a good piece of information already. So let's go here to 1, and we'll say here that our function is negative. So that's at the point x equals 1. Now let's go ahead a little bit. So let's look at f of 2. So that's going to be 2 cubed, which is 8, minus 3 times 2 squared. So that's going to be 3 times 4, which is 12. And then we've got to add 1 to that. So let's see, that's negative 4 plus 1. That's negative 3. So here at 2, it is also negative. So that actually does not give us any information about what's happening between 1 and 2. Because if the function is not changing sign, then it does not have to go through 0. Now let's maybe look at f evaluated at 3 and see what we get. So we got 3 cubed, which is 27. 3 times 3 squared, which is also 27, plus 1. So notice that's going to be equal to 1, which is positive. So here at 3, we plug that into the function and we get a positive number. So what that tells us is that we have a root on this interval from 2 to 3. And now we're not going to prove this carefully, but it's like quote unquote easy to see that everywhere past 3, this function is always going to be positive. So let's maybe notate this by putting an arrow in that direction. So this function is going to be positive everywhere after 3. You can check that if you want to carefully, maybe noticing that it's positive here and then it'll be an increasing function after that. That's pretty easy to show. But that means that our alpha lives on that interval 2 to 3. Okay, so now let's maybe look for some other places for other roots. Okay, so let's maybe notice that if we plug in 0, so f of 0 is equal to, well, that's 0 minus 0 plus 1, so that's 1. So let's put maybe 0 right here. And since we have 0 right there, well, and that is also positive, we know that there is a root between 0 and 1. But maybe we can get a little bit closer here. Let's maybe plug in f of a half. So f evaluated at half, what do we get for that? So that's going to be 1/8 minus 3/4 plus 1. Now let's notice that that number is positive because we have 1 minus 3/4 is 1/4 plus 1/8. So that's going to be something like 3/8. So this is 3/8, which is positive. So let's maybe go over here to 1/2. I'll maybe put it like this. And here we know at 1/2, this is positive. So we've narrowed it down. Our other root, well, one of our other roots is between 1/2 and 1. So let's maybe go one more and notice if we plug in f of 3/4, what are we going to get? So we're going to get 27 over 64. So that's 3 cubed over 4 cubed minus 27 over 16 plus 1, like that. Okay, so let's see what that simplifies to. So we can give this a common denominator by multiplying this by 4 and this by 4. And that's just a routine calculation, and what you'll end up with is that this is equal to negative 17 over 64. So let's maybe put that in here. Here we have 3/4, and we found out that the function was negative at 3/4, which tells us we've got another root in this spot right here. So let's see what we've got. We've got one root between 2 and 3, another root between 1/2 and 3/4. Now let's move to the left of 0. So let's maybe plug in -1. So f of -1 is going to be equal to -1 minus 3 plus 1. Well, notice that's going to be equal to -3, which is most definitely negative. So if we go over here to -1, we see that our function is negative, so that means we've got a root between -1 and 0. But like we did before, let's kind of try to ooch in on that so we can get a better idea. So let's maybe look at f of -1/2. And f of -1/2, well, that's going to be -8 minus 3/4 plus 1. But notice 1/8 and 3/4 makes 7/8. So all in all, this turns out to be 1/8, which is positive. So here at -1/2, we see that this guy is positive, which means our third root is going to be between -1 and -1/2. Okay, let's maybe go one more. Let's go -3/4. So if we do f of -3/4, that's going to give us minus 27 over 64, and then minus 27 over 16 plus 1. But notice that's clearly going to be negative because that essentially looks like this object right here, but we've got another negative term there. So here we'll get that this is less than 0, which tells us that at this point right here, -3/4, our function is negative, and thus our third root needs to be between -3/4 and -1/2. So maybe we could call this root beta, and we could call this root gamma. So we know that our goal largest root is between 2 and 3, but then our smaller roots are between -3/4 and -1/2, and 1/2 and 3/4. Okay, let's clean up the board and then we'll start from that. Okay, so we did a bunch of like hand calculation on the last board. We ended up with the fact that we can factor x³ minus 3x squared plus 1 as x minus alpha times x minus beta times x minus gamma. Alpha, beta, and gamma are the roots. Alpha is the largest one. It's between 2 and 3. Beta is next largest. It's between 1/2 and 3/4. And finally, gamma is between -3/4 and -1/2. Now we're going to see how we can use these three roots together to calculate this object right here. And you might say, well, why do we need to use the three roots together? And we'll see why. So let's maybe use this fact first. And that is for all natural numbers n, we have alpha to the n plus beta to the n plus gamma to the n is an integer. So now why? Maybe let's do just a little proof of this. So notice alpha to the n plus beta to the n plus gamma to the n is symmetric in all permutations of alpha, beta, gamma. So if we switch alpha with beta with gamma, or whatever, any way that we shuffle around alpha, beta, and gamma, alpha to the n plus beta to the n plus gamma to the n will remain unchanged. So that's easy to see. So what that tells us is that we can write alpha to the n plus beta to the n plus gamma to the n in terms of the elementary symmetric polynomials in alpha, beta, and gamma. So that's alpha plus beta plus gamma, alpha beta plus alpha gamma plus beta gamma, and then finally alpha beta gamma. Okay. But because we know the coefficients of our polynomial, we know the values of these. So notice that alpha plus beta plus gamma, well, that's going to be equal to 3. Again, because of one of our hints, and also just look at the coefficient of x squared on both sides of this equation. Then this combination right here is going to be equal to 0. And then finally, this combination right here is going to be equal to -1. So we know the sum of alpha, beta, gamma. We know this like twofold product of each one with the sum. And then we know the product of alpha, beta, and gamma. And those are all integers. So like I said, I think this is well known. You wouldn't need to prove this on the test, but you would maybe need to at least say something about symmetric polynomials or whatever to show that you are stating the correct facts. Okay, so we've got this alpha to the n plus beta to the n plus gamma to the n is in the integers, and that's for all natural numbers n. So our second fact will go like this. For n large enough, and we'll talk about exactly what size it needs to be, and we'll see that large enough doesn't actually have to be that large in this case. We have beta to the 2n plus gamma to the 2n. So in other words, the sum of some even powers of beta and gamma, that's always going to be between 0 and 1, not including 0 and not including 1. Well, it clearly doesn't include 0, because if you take these both to even powers, you're going to be summing two positive numbers. Now let's see maybe why it can't equal 1. So let's maybe look at n equals 1. So that would be like 2n equals 2. And so we've got beta squared plus gamma squared. And we can see, well, that's clearly bigger than 0 like we just talked about, but it's going to be less than 3/4 squared plus -3/4 squared. Because 3/4 is going to achieve the maximum value of beta, and -3/4 is going to achieve the maximum value of gamma squared. Okay, so let's see what that gives us. That gives us 9/16 plus 9/16, which is equal to 18/16. Well, 18/16 is bigger than 1, so this is not quite large enough. So in other words, n equals 1 doesn't work here. But let's maybe look at n equals 2. So if we take n equals 2, we have 0 is less than b to the, and I'm going to put 2n here plus gamma to the 2n, which is less than or equal to beta to the 4th plus gamma to the 4th. Well, if we raise it to some power that is bigger than 2, so let's maybe put here n is bigger than or equal to 2, then that means here we have beta to the 4th plus gamma to the 4th, or larger powers. So let's see, that is going to be less than 3/4 to the 4th plus -3/4 to the 4th. Okay, but what does that end up being? Well, I think 4 to the 4th is going to be 256. So we've got 81 plus 81 over 256, but that's most definitely less than 1. So we showed that beta to the 4th plus gamma to the 4th is on the interval 0 to 1. But then all larger powers of beta to the 2n plus gamma to the 2n are smaller than or equal to this beta to the 4th plus gamma to the 4th. So those are between 0 and 1 as well. Okay, so let's maybe keep those two facts, bring them to the top, and then we'll move on to the next step. Okay, we've done a bunch of stuff so far. We did some stuff with finding out where the roots of this polynomial lie along the real line, from largest to smallest. Then we argued a couple of pretty simple facts, and those were for all n bigger than or equal to 2, alpha to the 2n plus beta to the 2n plus gamma to the 2n is an integer, and beta to the 2n plus gamma to the 2n is on the open interval 0, 1. So we want to use these two facts to get a handle on this floor of alpha to this power, but we're going to do it for a general power, well, an even power for our case. So let's maybe make the following observation. So let's see, the floor of alpha to the 2n, and so here we're simultaneously using the fact that these three sum to an integer, and that these two sum to a number between 0 and 1. So the floor of alpha to the 2n is going to be equal to alpha to the 2n plus beta to the 2n plus gamma to the 2n minus 1. So that finishes off the first round of analysis of this problem. Now we're going to finish it off by working mod 17 and then using Fermat's little theorem. So I want to maybe notice that mod 17, we can factor x cubed minus 3x squared plus 1 in the following way. So x cubed minus 3x squared plus 1 is going to factor like x minus 4 times x minus 5 times x minus 11. So I'll just put equals, or maybe I should put congruent mod 17. Or this is really, if you're into this kind of stuff, equality in the field of 17 elements adjoin x. In other words, the polynomial ring with coefficients in the field of 17 elements. You can think of it like that as well. Okay, and maybe how would we figure out this factorization? Well, there's a theorem in number theory or abstract algebra that says mod p, a polynomial can only have as many roots as its degree. So that's really similar to what's happening in the real numbers. And then you can just check numbers between 0 and 17 to find which ones are roots. And you'll see that if you plug 4 into this equation, you get 0 mod 17. If you plug 5 into this equation, you'll get 0 mod 17. In other words, a multiple of 17. And then the same thing for 11. Great. But now notice that tells us the following. So combining these two approaches together, we will see that alpha to the 2n plus beta to the 2n plus gamma to the 2n is going to be congruent to 4 to the 2n plus 5 to the 2n plus 11 to the 2n mod 17. Again, that's just doing those two approaches together. Now, next what we can do is maybe look at this thing mod 17. So that tells us that alpha to the 2n, the floor of that is going to be congruent to 4 to the 2n plus 5 to the 2n plus 11 to the 2n minus 1 mod 17, like that. And so that means that all we need to check is alpha to the 1998. And then let's see what that means. That means we need to calculate 4 to the 1998 plus 5 to the 1998 plus 11 to the 1998 minus 1 mod 17. And hopefully that's congruent to 0 mod 17, because that means it would be a multiple of 17, which is our whole goal. Okay, so let's maybe clean up most of the board. We'll start from this point. We've got one last calculation to finish this off. And that is, we need to calculate 4 to the 1998 plus 5 to the 1988 plus 11 to the 1988 minus 1 mod 17. So we're going to use two fairly simple facts in order to do that quickly. And one is, by the division algorithm, we can write 1988 as 124 times 16 plus 4. And then using Fermat's little theorem, we know that anything to the 16 power is going to be congruent to 1 mod 17, which tells us that a to the 1988 is going to be congruent to a to the 4 mod 17. And this is obviously true if 17 does not divide a, but it doesn't divide any of these bases, so we're good to go there. The next thing that we're going to do is, since 11 is more than half of the way to 17, we might as well write it as -6 mod 17. Then the calculation will be a little bit easier. Now we're ready to jump into it. So let's notice that we have alpha to the 1988, the floor of that. So that's going to be congruent to, well, let's see, we're going to have 4 to the 4 plus 5 to the 4 plus -6 to the 4 plus minus 1 mod 17, by these two facts up here and the results from all of our previous calculations. Okay, now next we can take this 4 to the 4, and maybe we can notice that that is going to be 16 squared, but the next 5 to the 4, so we can write that as 25 squared, and then -6 to the 4, so that's going to be 36 squared minus 1 mod 17. But we might as well reduce all of these mod 17 just for simplicity. So let's check it out. That's going to be equal to -1 squared, because 16 is -1 mod 17. And then 25, well, that's equal to 8 mod 17. That's because it's 8 more than 17. And then 36 is 2 mod 17. So here we have 2 squared minus 1 mod 17. And now we're essentially home free. We can see that -1 squared is 1. That's going to cancel with this 1 here. And then we'll have 8 squared is equal to 64. So here we have 64 plus, and then this guy is 4. This is all happening mod 17, but that is congruent to 68 mod 17. But then you can check that 68 is a multiple of 17, so that makes this thing congruent to 0 mod 17. So now looking at this extreme left-hand side, we have the floor of alpha to the 1988 is congruent to 0 mod 17, which shows us that this floor of 1988 is divisible by 17. And that's a good place to stop.